We live in an era where AI can write code, compose poetry, and converse like a human, leading many to believe it possesses a soul. But the truth is both simpler and more profound. Beneath this futuristic intelligence lies the act of rolling dice millions of times at the speed of light. Welcome to the third pillar of Bangsaen AI Studio. Today, we decode the brain of AI with the mathematics of probability.
Have you ever just stopped and thought about how wild modern AI is? I mean, you ask it to write a poem, and poof, there it is. You tell it to debug your code, and it finds the mistake. It really feels like we're talking to some kind of thinking machine. But what's really going on inside that digital black box? Well, to find the answer, we're not going to look to the future. We have to go deep into the past. Seriously, how does it go from being just a blank slate to a partner you can have a conversation with? The answer is way more surprising and honestly a lot more elegant than you might think. It's this incredible story that connects the foundational ideas of a brilliant mathematician from the World War II era to the very engine that powers the tools we use every single day, like ChatGPT. So, the first part of this big reveal is a journey back in time. And we're not just hopping back a few years or even to the dawn of the internet. Nope, we gotta go way, way back, all the way to the 1940s to find the true blueprint for the AI we're all using today. Okay, so picture this. It's 1948. A genius mathematician and engineer named Claude Shannon publishes this paper that would, and this is no exaggeration, lay the foundation for our entire digital world. And get this, he wasn't trying to build an AI. He was just trying to figure out how to send messages clearly over those old, noisy telephone lines. But in doing that, he accidentally gave us the fundamental language for understanding information itself. Shannon's huge idea was to completely split information from its meaning. See, for him, information wasn't about what a message says. It was all about how much uncertainty it gets rid of for the person on the other end. It was a totally radical idea that turned information into something you could actually measure. So, how on earth do you measure something as fuzzy as uncertainty? Well, Shannon gave us two super powerful tools that became the bedrock for everything that came next. First up, he gave us the bit. Now, we all know a bit as a 0 or a 1 in a computer, right? But for Shannon, oh man, it was so much deeper. 1 bit is the exact amount of information you need to answer a yes or no question where both answers are equally likely. In other words, it's what you need to cut your uncertainty in half. Let's make this real. Think about a guessing game. If you're trying to guess a number between 1 and 100, asking, is it 1, is a terrible strategy. But asking, is it less than 50? Now that's a genius move. Why? Because no matter what the answer is, you've just wiped out half the possibilities. Bam! You just gained exactly 1 bit of information. If you keep doing that, you can find any number in just 7 questions, because each question slices your search space right in half. Right, but what about when things aren't so neat and tidy? Not a perfect 50-50. That's where Shannon's next big idea comes in: entropy. In information theory, entropy is really just a way to measure the average unpredictability, or surprise, of something. A super predictable event has low entropy, a totally unpredictable one has high entropy. Simple as that. So, like a two-headed coin, that has 0 entropy. There's no uncertainty, no surprise at all, right? A biased coin that lands on heads 90% of the time has really low entropy. You're not very surprised when it's heads. But a fair coin, that has the absolute maximum entropy you can get from 2 outcomes, a full 1 bit. It is perfectly unpredictable. Okay, I hear you. Measuring coin flips is cool and all, but what does this have to do with AI? Well, the next step is connecting this whole idea to something we all use constantly: data compression. So what's a .zip file actually doing when you use one? It's scanning for patterns and repeated stuff in your data and then creating a shorthand for it all, which makes the file smaller. Shannon's work proved that the absolute best you can compress something is limited by its entropy. And here's the crazy part. In a way, an AI language model is doing the exact same thing. It compresses all of human language by finding the rules, the patterns, the relationships, and storing it all in its network. So this whole idea that learning is basically just super advanced compression, that leads us right to the core task of every single large language model, playing an endless game of guess the next word. You know this sentence. We all do. Our brains, which have spent our whole lives compressing the patterns of English, instantly know what's coming next. So what word popped into your head? I'm going to bet it was dog. The AI is trying to do the exact same thing your brain just did. But here's the thing, the AI doesn't just spit out one word, it gives a whole probability distribution across every single word it knows. You can see it's pretty sure the answer is dog, but it also knows that other words are, technically possible. This whole list of probabilities, that's the AI's best guess about what reality looks like. But how does it learn to make that guess better? And this, my friends, is where it all comes together. The AI is trained using something called cross-entropy loss, and this is a direct descendant of Shannon's entropy. It basically measures the surprise the model feels when you show it the right answer. If it predicted dog with 70% confidence and the real answer was dog, its surprise is low. But if the real answer was car, its surprise would be through the roof. All that surprise gets calculated and crunched down into just one single number. We call it the loss score. This one number tells the entire model how wrong its prediction was. The higher the number, the more surprised and the more wrong it was. The goal of all its training is to get this number as low as humanly or artificially possible. And that simple idea, just calculating a surprise score, that is the engine. The absolute engine that drives the whole learning process for every single modern transformer AI. So the whole process is this beautiful, elegant loop. The AI makes a guess, it checks the real answer, and calculates its surprise. That's the loss score. Then, this super clever algorithm called backpropagation, it takes that one number and works backward, tweaking all of its billions of connections just a tiny bit, basically asking, how can I be a little less surprised next time? Now, you just do that trillions of times with a mountain of text, and you end up with an AI that is freakishly good at predicting the next word. So isn't that incredible? What started as a theory to get clearer phone calls back in 1948 has become the fundamental blueprint for some of the most advanced tech we have today. It's just this straight, unbroken line of thinking. Shannon's bit gave us a way to chop up uncertainty. His entropy gave us a way to measure it. And from that, we derived cross-entropy, a way to measure an AI's surprise, which became the very loss function that lets it learn. An idea from 1948, literally powering the technology of today. It's amazing. So this leads to a really important way of thinking about all this. When we talk to an AI, we're not talking to an artificial mind. We're interacting with the world's most sophisticated pattern-matching machine. It's the ultimate uncertainty-reducing machine, whose entire existence boils down to one simple goal: lower its own surprise about the world based on the data it's seen. And that kind of leaves us with this one last big question. If building this incredibly powerful artificial intelligence is, at its core, just about creating a model to minimize surprise and reduce uncertainty about the world, what does that say about us, about the processes happening inside our own brains every single day?
Claude Shannon gave us the unit of measure, teaching us that information is simply the resolution of uncertainty. But the question remains, how do we use this theory to predict the future? If I say the word hello, can you guess what comes next? This is the genesis of the world's first language model, one that didn't use neural networks, but used simply counting.
Have you ever just stopped and wondered how your phone knows exactly what you're about to type? It feels like magic, right? Well, it's not. It's math. And it all starts with one surprisingly simple idea. So let's dive right in. We're going to break down the very first step in how machines learn to understand language: simple probability. But before we get into the numbers, let's start with a little puzzle. This puzzle really shows why language is so incredibly tricky for a computer to get right in the first place. Okay, so what you're looking at is a phrase in Thai. Now, for a person, context is everything. But a computer, it just sees a string of characters. And here's the real kicker. Thai script doesn't always put spaces between words. So for a machine, the big question is, where does one word end and the next one begin? And this is what's so wild. That one little phrase could be broken up to mean a round eye, or you could break it up a different way and it means to be exposed to the wind. I mean, those are two totally different ideas coming from the exact same set of letters. So how in the world does a machine, which has zero intuition, make the right call? Well, it can't rely on gut feelings. It has to rely on math. It asks a really basic question. Which of these options is statistically more likely to show up in the real world? And that is where our journey into probability really kicks off. To really get how we can apply probability to something as messy and complex as language, we've got to build up our toolkit with some simpler ideas first. So we're going to start with the absolute basics. We're going to take a quick 3-step journey. First, we'll look at a simple dice roll. Easy enough. Then we'll level up just a bit to a jar of colorful marbles. And finally, we're going to connect all of that to language with a concept called a bag of words. Each step builds right on top of the last one. All right, step 1, the dice roll. You definitely remember this from school, right? The probability of something happening is just the number of ways it can happen divided by the total number of things that could happen. So, with a normal 6-sided die, the chance of rolling, say, a 4 is just 1 out of 6. Simple. But here's the really important part. The real world is almost never like a perfectly fair die. Think about language. The word the shows up constantly, way more than a word like, I don't know, xylophone. Their probabilities are not equal at all. So how do we deal with that messiness? And that brings us to step 2, the marble jar. So imagine we've got a jar with 55 marbles. Now, the chances aren't equal. You can see there are a ton of red ones and only a few blue ones. But what's so cool is that the same simple formula still works. The probability of picking a red marble is just its count, 30, divided by the total, 55. We're not doing any fancy math, we're just counting. Okay, get ready because this is the big jump. We're going to take that exact same logic from the marble jar, just simple counting, and apply it directly to words. This is how we build our very first super simple language model. And here is the core idea, the whole aha moment. A bunch of text, which we call a corpus, is nothing more than a giant jar of marbles. Seriously. But instead of counting red, green, and blue, we're just counting words. Let's use this tiny little bit of text as our jar. Just 2 sentences. I am a student. I am happy. If we count them all up, including the periods, we have a grand total of 9 words. Or you could say 9 marbles in our jar. And check this out. We can build a probability table for our words that looks exactly like our marble table. The word I shows up twice, so its probability is 2 out of 9. The word happy only shows up once, so its probability is 1 out of 9. See? We're just counting how often things appear. This simple model is called a unigram model, or I think a better name for it is a bag of words. But to make this work, this model makes one giant, and I mean giant, assumption. It's called the unigram assumption, and it basically says that the probability of any word depends only on its own frequency. It totally ignores all the words around it. And that's why bag of words is such a great name. It's like we threw all our words into a bag, shook them up. The order just doesn't matter at all. So there we have it. We've built our first language model. It's simple, yeah, but it's a real start. Now it's time to see why this is only step 1. Let's put this thing to the test and find its biggest, most critical flaw. So let's ask a really important question. Given that this whole model is built on ignoring word order, is it anywhere near smart enough to know the difference between a real sentence and just a random jumble of words? Okay, let's calculate the probability for 2 phrases using our model. Over on the left, we've got the correct sentence, I am happy. We just multiply the probabilities of each word together. And on the right, we have the nonsense version, happy am I. We do the exact same calculation. You see what's happening here? The probability is identical. Our model thinks that I am happy and happy am I are equally likely. It assigns the same score to a proper sentence and to complete gibberish. Why? Because it's just a bag of words. It has 0 concept of grammar. That is a huge problem. And you know, that's not even the only issue. What happens if we ask our model about the word sad? Well, it wasn't in our original 2 sentences, so its count is 0. The model literally thinks the probability is 0, as in sad is an impossible word that can never happen. This shows another huge weakness. These super simple models need just a mind-boggling amount of text data to be even a little bit useful. But this critical flaw, this total inability to see context, isn't the end of the story. Actually, it's the opposite. It's the very problem that forced researchers to come up with the next big breakthrough. And here is that breakthrough idea. A useful model can't just ask about a word all by itself. It has to start asking a smarter question. It has to ask, what's the chance of seeing this word given the specific word that came right before it? And this really shows you the leap we're about to take. We're moving from step 1, which just asks, what's the probability of the word am? And we're moving to step 2, which asks a much more powerful question. What's the probability of am, given that the last word we saw was I? This is the huge shift from simple probability to something called conditional probability. And that, of course, leaves us with the big questions for next time. How exactly do we calculate these new conditional probabilities? And, more importantly, does adding just this one little piece of context actually fix that huge grammar problem we just found? Well, that is exactly what we are going to dive into in step 2. See you then.
Engrams demonstrated the power of statistics, but they have limits. Computers do not understand letters. They don't understand love or hate. They only understand numbers. Before we can teach AI to comprehend language, we must slice language into pieces the machine can digest. This process is akin to turning literature into a barcode. We call this tokenization.
You know all that AI magic we see everywhere? Well, today we're going to pull back the curtain on something that happens before any of that. It's this hidden fundamental step, and honestly, without it, things like ChatGPT just wouldn't work at all. So here's the big question, right? Computers, they only get numbers, zeros and ones. So how on earth do they take our words, our messy, beautiful, chaotic language, and turn it into something they can actually compute? Well, the answer to that puzzle is a process called tokenization.
Okay, so here's our game plan for this journey. We're going to start with the absolute basics, the atoms of AI language. Then, we'll dive into a huge problem that stumped researchers for ages. After that, we'll see the brilliant breakthrough that changed everything, and how that one idea basically unlocked the modern AI we have today. And finally, we'll peek into the future and see what's next in this incredible hidden world.
All right, first things first, let's get to the why. Why do we even need to do this? What's the point? So this whole process is called tokenization. And honestly, the best way to think about it is that tokens are like the atoms of language for an AI. You see, a model can't do math on the letters CAT, but it can do math on a number, say 589, that stands for the token cat. Tokenization is that first, absolutely critical step of smashing our language down into these tiny, countable numerical atoms.
Okay, let's make this super concrete. Check this out. We start with a plain old sentence. We feed that text into a machine called a tokenizer. And what does it do? In this simple case, it just chops the sentence up by words and punctuation. And boom, the output isn't a sentence anymore. It's a neat, tidy list of these little atomic units, these tokens. And now they're ready for the real work.
And this is where it gets really, really important. This isn't just some boring data cleaning step. No way. The tokenizer literally defines the model's entire worldview. Think about it. If n-grams is treated as one single token, one single atom, then the model can never understand what n means or what grams means on their own. It is completely, totally blind to anything happening inside that token. Okay, so it sounds simple, right? Just chop up the words. But how you choose to chop them up, how you define those atoms, well, that created a huge dilemma for early researchers. They basically had two paths they could go down. And here's the kicker. Both of them seem to lead straight to a dead end. So on one hand, you could do what's called word-based tokenization. Simple enough. Every token is a full word. That's awesome for capturing meaning. But your dictionary, your vocabulary, would need to have millions of words. That's just gigantic. Then, on the other hand, you could go with character-based tokenization. Now your dictionary is super tiny, right? Just the ABCs and a few symbols. But the problem is, a single letter like T or O carries almost zero meaning by itself. Plus, it makes your sentences incredibly, ridiculously long for the model to read. That first approach, the word-based one, had a truly fatal flaw. It led to something called the out-of-vocabulary crisis, or OOV for short. So imagine this. You've trained your model. It has its big dictionary of words. What happens when it stumbles across a word that's not in its dictionary? A word it has never, ever seen before. I mean, think about it. New names, new slang, new tech. Words that literally didn't exist when the model was being trained. Words like, I don't know, Zendaya, or even ChatGPT itself. To an older model, these words would be complete gibberish, totally alien. So what could the model do? It had only one option. It had to lump
every single new word it saw into one generic, useless category, a single token, UNK, which, yeah, just stands for unknown.
And this is just a catastrophic loss of information. I mean, this isn't a small mistake, it's a complete and total failure. The model looks at the name Zendaya and the word ChatGPT and sees the exact same meaningless blob. All that unique, rich information in the new word, it's just poof, gone. This whole dilemma, this OOV problem, it really held the entire field of AI back for years. That is, until a really clever, revolutionary idea came along and offered a beautiful, elegant solution.
So, instead of that all-or-nothing choice between whole words and single characters, researchers came up with this brilliant compromise, subword tokenization. The idea is actually pretty simple. Common words like and or the, they can just stay as their own single tokens. But the rare words, the weird words, the new words, those get broken down into smaller, meaningful chunks.
Let's take a word like annoyingly. A subword tokenizer is smart enough to see that and break it into two pieces it probably already knows: the common word annoying and the very common suffix ly. All of a sudden, the model has a fighting chance. It can figure out the meaning of this new, complex word by looking at its component parts, which it already understands. And this solved everything. The out-of-vocabulary crisis? Gone. Any new word can just be built from smaller pieces. That giant multi-million word dictionary? Nope. Now we have a compact, manageable vocabulary. We keep the meaning because the subwords themselves are meaningful. And maybe the coolest part? These tokens aren't based on some linguist's rules anymore. They're learned automatically, statistically, just by having an algorithm chew through mountains of text data.
Okay, so what? Why are we spending all this time on this one clever trick? Because this, right here, subword tokenization, is the key that unlocked the entire modern era of AI. It's the thing that made the transformer architecture, the engine behind models like GPT, not just good, but actually possible to build.
Okay, here's why. Deep inside a transformer model, there's a thing called an embedding layer. You can just think of it as a giant dictionary, a lookup table, that stores the meaning for every single token the model knows. And here's the catch. That table has a fixed size. It can't grow. So how do you represent our infinite, ever-changing human language inside a finite box? Well, subword tokenization is the only way to do it.
But wait, there's an even bigger, more mind-blowing reason. The real magic of a transformer is its attention mechanism. But this magic comes at a steep price. The computational cost, the sheer processing power it needs, grows exponentially. Specifically, it's n squared, where n is the number of tokens in your sentence. This means a longer sequence of tokens isn't just a little bit more work, it is dramatically, insanely more expensive to process.
Now, let's put that into perspective. Look at this. If you took a 100-word sentence and used the old character-based method, you might end up with a sequence of, say, 500 tokens. But with our clever subword method, that same sentence might only be 25 tokens long. That is a 20 times reduction in the length of the sequence, 20 times shorter.
And now for the payoff. Remember that n squared cost? If you make your sequence 20 times shorter, you don't make the calculation 20 times cheaper. Oh no. You make it 20 times squared times cheaper. That's 400 times cheaper. That's the ballgame right there. This wasn't just a small improvement. This was the engineering breakthrough that made training these gigantic models affordable and practical in the first place.
But, the story doesn't just end there. Even this incredible, revolutionary solution isn't perfect. And researchers right now are wrestling with some of its more subtle, but really important flaws.
You see, because this whole process is statistical, it's just an algorithm finding patterns. Sometimes it creates really weird, awkward, or just plain rare tokens when it sees strange data. Researchers have a name for these: glitch tokens. And it turns out, these tiny little mistakes at the atomic level can act like poison for the AI, causing it to do unpredictable, bizarre things, including the hallucinations we hear so much about.
And that leaves us with a really fascinating and kind of scary final thought. We've seen that tokenization creates the very atoms of an AI's language, the building blocks of its entire understanding of our world. So the question is, if those atoms themselves are flawed, if they have these little glitches baked in, then how reliable is the reality that the AI is building with them?
Now we have numbers, but those numbers are still empty. The number 1 and the number 100 have no semantic relationship. So how do we teach a computer that king is related to queen? The answer isn't in the definition, it is in the location within space. Prepare to enter a dimension where mathematics transforms into meaning, inside the world of embeddings.
How do you teach a computer what a word actually means? Today, we're diving into one of the coolest, most elegant ideas in all of modern AI. It's a journey that's going to take us from just, simple counting, all the way to creating a true map of meaning right inside the machine.
Okay, so let's just kick things off with a puzzle that seems, well, kind of impossible. How on earth can a computer solve this kind of word algebra? I mean, it seriously looks like magic, but I promise you, by the time we're done here, you're going to know the secret. Let's get into it.
All right, first up, words versus numbers. This right here is the fundamental challenge at the heart of pretty much all of natural language processing.
See, it all comes down to this one simple problem. We humans, we communicate with words. Computers, they only speak the language of math, of numbers. So how in the world do we bridge that massive gap? How do we take a word, like cat, and turn it into numbers a machine can actually understand and work with?
Well, the first idea that probably pops into your head is something called one-hot encoding. And you know what? It's super intuitive. Just imagine you have a dictionary with, say, 50,000 words. We give every single word a unique ID number. So maybe cat is word number 123. Its representation then becomes this gigantic list, a vector of 50,000 zeros with just one single one flipped on at that 123rd position. Seems simple enough, right? Well, it turns out this simple solution is a complete and utter catastrophe.
Yeah, this isn't just an inefficient way of doing things. It's a total conceptual dead end. It creates what's known as a semantic void, basically a space where meaning just can't exist.
So this approach has two, absolutely fatal flaws. The first one is practical. It's called the curse of dimensionality. These vectors are massive and almost completely empty, which is a total nightmare for computers to process. But the second flaw, man, that is the real deal breaker, the semantic void. With this system, the computer has absolutely zero understanding of how words relate to each other.
And if you look at the math, it just lays the whole problem bare. When you use a standard technique to measure the similarity between these vectors, the result for any two different words is always zero. This tells the computer that they are completely separate with no connection whatsoever. So get this. This is the kicker. In the computer's mathematical world, the connection between cat and dog is identical to the connection between cat and car, which is to say, there is no connection. None. They're all just totally unrelated islands of information. If your goal is to understand language, this is an absolute disaster.
Okay, so clearly that's a dead end. To get out of this void, we need something totally different. We have to stop just assigning random IDs and start actually learning a true map of meaning. And that is where word embeddings come in.
And you can really see the massive shift right here. We're going from those enormous, mostly empty vectors down to these much smaller, dense ones, where every single number actually holds a piece of the meaning. And here is the absolute key. Semantic meaning isn't missing anymore. It's captured by how close the vectors are to each other in this new map. For the first time, similar words actually look similar to the computer.
So how in the world do we create this map, right? How does a machine learn which words should be close together? Well, the core idea, believe it or not, doesn't come from computer science. It comes from linguistics.
It all comes down to this famous quote from back in 1957, "You shall know a word by the company it keeps." And that's really the heart of it all. The meaning of a word isn't just some abstract dictionary definition, it's defined by the other words you usually find hanging around it. Words like cat and dog show up in similar contexts, with words like pet, food, and walk, while a word like car hangs out in a completely different neighborhood of words.
We use this idea with a really clever trick called a fake task. We train a neural network on a simple goal. We give it a bunch of words and ask it to predict the word in the middle, or we give it the middle word and ask it to predict its neighbors. But here's the thing. The network itself isn't what we're after. The real magic happens as a side effect. To get good at this prediction game, the network is forced to learn really good internal representations for each word. Once it's trained, we just throw away the network and keep those juicy learned representations. Those are our word embeddings.
And this is where it gets really mind-blowing. Once we have these learned vectors, this map of meaning, something truly incredible emerges. We can start doing math with words.
So what actually happens if we take these vectors, these long lists of numbers that somehow capture meaning, and we just do basic arithmetic on them? Add and subtract them.
Let's go all the way back to that puzzle from the beginning. We take the vector for king, we subtract the vector for man, and then we add the vector for woman. What do you think we get?
It's incredible. The vector that pops out is the one that is closest in this whole meaning map to the vector for queen. The math just works. It's like by subtracting man from king, we isolated the pure abstract concept of royalty. Then we just added that concept of royalty onto woman, and bam, it landed right on queen.
And this right here, this is maybe the most important part of this whole story. The model was never taught about kings or queens or gender roles. No one programmed that relationship in. This ability to solve analogies is an emergent property. It just appeared, naturally, from the simple task of learning which words hang out together. This is the proof that the model didn't just memorize things. It actually learned the underlying structure of their relationships.
And this isn't just some cool party trick, right? This is the engine that powers so much of the AI you use literally every day. It's how a sentiment model knows that wonderful and fantastic mean pretty much the same thing. It's why a recommendation engine can suggest an article on deep learning when you've just been reading about neural networks. The system gets the relationship, not just the keywords.
But as amazing as this all is, this method has one big flaw. And it's a flaw that actually paved the way for the next giant leap in AI, leading us right to the models that we have today.
The problem has a fancy name, polysemy, but all it really means is that words can have multiple meanings. Think about the word bank. In the system we've described so far, bank gets exactly one vector. That single vector becomes this weird, mushy average of all its meanings, mashing together riverbank and financial bank into one confused representation.
And that leads us to our final big question. How can a single static vector possibly capture two totally different ideas? Well, the short answer is it can't. Not very well anyway. And it was that limitation, that exact problem, that forced the entire field to evolve.
So this brings us full circle. Everything we've covered today, these are called static embeddings. One single, fixed vector for each word forever. The next great leap was creating contextual embeddings, where the vector for a word like bank is generated on the fly and it's different depending on the sentence it's in. But here's the final kicker. These static embeddings we've been talking about, they aren't obsolete. They are the essential input layer for modern AI, like transformers, which then generate that powerful contextualized output. And how that works? Well, that's a story for another explainer.
Embeddings gave words meaning, but they had a fatal flaw. The word bank could mean a riverbank or a financial bank. Classic embeddings couldn't tell the difference. AI needed a mechanism to focus its attention on context, a mechanism that changed the history of AI forever. In 2017, Google revealed an architecture named the Transformer.
Have you ever just stopped and wondered how an AI like ChatGPT actually gets what you're saying? I mean, it really feels like magic, right? But it's not. It's the result of this incredible journey, a story that's packed with dead ends and these absolutely brilliant breakthroughs. So today we're going to pull back that curtain and really dig into the story of how machines finally learn to speak our language. So here's the game plan. Our story kicks off with something called the whispering chain problem, which, believe me, almost stopped AI dead in its tracks. Then we'll see how a roundtable revolution just completely changed the game, which then split into 3 different ways of thinking. But of course, that created a new, massive problem, a huge cost wall. And that brings us to right now, where we're at this fascinating crossroads between 2 futures, one built for massive, massive scale, and the other for just pure raw speed. All right, let's dive right in at the very beginning. So the first giant hurdle for AI was something that we humans do without even thinking about it, understanding context. How can a machine possibly know that the exact same word can mean 2 totally different things? It sounds so simple, but for the first AIs, this was a massive, almost impossible challenge to overcome. I mean, just take the word bank. For you and me, it's easy, but early AI used something called static embeddings, which basically means the word bank was just one single mathematical idea. The AI was literally blind to the words around it. It had no way of telling the difference between a financial institution and the side of a river. So the first real attempt to solve this was the recurrent neural network, or RNN. And honestly, the best way to think about it is like that game of telephone or whispering chain. The first word gets processed, and a little summary of it is passed to the second word. That second word adds its own meaning and passes a new summary to the third, and so on. You can probably already see the two fatal flaws here, right? First, by the time you get to the end of a long sentence, that original message from the first word is fuzzy, distorted, or just gone. And second, processing things one at a time was just painfully slow. The entire field was just stuck on this one word at a time problem. And then, in 2017, this paper comes along with an idea so radical, it sounded almost crazy. What if we just threw the whole chain concept away entirely? The paper was called Attention is All You Need. And that wasn't just some catchy title. It was a declaration of war on the old way of doing things. It introduced a brand new architecture that was about to change absolutely everything, the transformer. Okay, so if an RNN is that whispering chain, a transformer is a round table. At this table, every single word can see and talk to every other word in the sentence at the exact same time, all at once. Suddenly, no word is ever too far away to be forgotten, and the whole process can happen in parallel, which makes it unbelievably fast. In one brilliant move, it solved both the memory problem and the speed problem. So how does this round table actually work? Well, it's this mechanism called self-attention, and a really great way to think about it is like a library search. For every single word, the model generates three things. First is a query, which is basically the question the word is asking. So for the word it, the query might be something like, hey, I'm a pronoun, who or what am I referring to? Second, every other word generates a key, which is like a label advertising what it is. The word animal might have a key that says, hi, I'm a noun. And finally, each word has a value, which is its actual meaning. The model just matches the best keys to the query and then blends their values together. And that's how it figures out it's talking about the animal. Now, this original transformer was a total game changer, but researchers pretty quickly realized that understanding language can mean different things. Like, are you trying to understand a sentence to classify it, or are you trying to understand it so you can generate a new one? This led them to basically break the transformer apart, creating three distinct families of specialists. So this created three specialized paths. First up, you've got the encoder-only models, like BERT. These guys are all about pure understanding. They're trained to play fill-in-the-blank, looking at text from both directions, which makes them amazing for things like search and analysis. Then you have the decoder-only models, like, you guessed it, GPT. They are all about generation. They're trained to do one thing, predict the next word. That makes them perfect for chatbots and creating content. And finally, you have the full encoder-decoder models, which are built to transform things. Think translating from one language to another, or summarizing a long document. Okay, so the Transformers roundtable attention thing, it felt like a superpower. It really did. But this incredible power came with a terrible, terrible price. The very mechanism that made it so effective, letting every single word look at every other word, was also its greatest weakness, its Achilles heel. This is known as quadratic complexity, and it is a brutal, brutal problem. Let me break it down for you. If you double the length of the text you're processing, the computational cost doesn't just double, it quadruples, 4 times the cost. And if you make the text 10 times longer, the cost doesn't go up by 10, it explodes by 100 times. This is the quadratic wall. It's the reason you can't just feed an entire book into a normal chatbot and expect it to work. It would be astronomically expensive. And for something like a chatbot, this creates this massive bottleneck in real time. To generate just the next word, it has to look back and reevaluate every single word that came before it in the conversation. It has to store the key and value for that entire history in its memory, in something called a KV cache. So as your chat gets longer, that cache just gets bigger and bigger, eating up precious memory and making the whole thing slower and slower. So the AI world was staring at this crippling wall. And this roadblock led to 2 major competing philosophies on how to smash through it. One path focused on finding a really clever way to scale up, while the other focused on a total redesign for pure, unadulterated speed. Okay, path number 1 is called Mixture of Experts, or MO. Think of it like a hospital system. A regular transformer is like one single, brilliant general practice doctor who has to see every patient for every single problem. Super smart, but totally overwhelmed. An MOE model, on the other hand, is like a giant hospital with dozens of different specialist departments. Then there's a really smart receptionist, called a router, who looks at each incoming patient, or in our case a word token, and sends it to only the 2 most relevant specialists. So you get access to the knowledge of the entire hospital, but you only pay the compute cost of visiting 2 doctors. It's an ingenious way to make models massively knowledgeable without making them impossibly expensive to run. Now, the second path isn't just a clever workaround, it's a full-blown revolution. A new architecture called Mamba doesn't even try to fix the transformer's quadratic bottleneck. It just throws it out the window completely. Mamba operates in linear time, and that means if the context gets 10 times longer, the cost just goes up 10 times, not 100. It's a fundamentally different way of thinking about the problem.
Now, it is really tempting to hear that and immediately call Mamba a transformer killer. But the reality, as always, is a little more nuanced. The future isn't about one winner take all. It's about a really fundamental trade-off between 2 very different ways of handling information: brute force recall versus intelligent compression. And this really gets to the heart of the difference. A transformer is a brute force machine. It stores every little detail in its memory cache, which is amazing if you need perfect recall. Mamba is the total opposite. It's all about intelligent compression. It's constantly summarizing the history of the conversation into a small, fixed-size memory state. This means it has to decide what's important to keep as it goes, which means it might forget some of the tiny little details along the way. So you see the trade-off: perfect, flawless memory versus incredible, mind-bending efficiency. And this table really puts it all together for us. The standard transformer, it gives you the highest possible accuracy, but it's incredibly slow and expensive for long text. Mixture of experts lets us build models with just a staggering amount of knowledge while keeping the running costs down, but it still suffers from that same underlying quadratic bottleneck. And then there's Mamba. Unbelievably fast, can handle almost infinite amounts of text, but it achieves that speed by compressing information, which makes it a little weaker at tasks where you need to copy something back perfectly, word for word. So, what's the real takeaway here? Well, the future isn't about finding one model to rule them all. It's about building a toolbox. Sometimes you're going to need that perfect, high-fidelity, brute force memory of a transformer. Other times, you're going to need the blistering, world record speed of Mamba to process a huge document. So the real question isn't which one is better. It's what incredible new problems are we finally going to solve now that we have the choice between perfect recall and infinite context?
From the probability of a coin flip in 1948 to ChatGPT today. This journey wasn't born of magic, it was born of probability engineering, but this is just the landscape view. In the next video, we will dive deep into the mathematics of each component, so you don't just remain a user of AI, but become a builder of it. Welcome to the digital institution.